There are 3 videos in the playlist. The video goes from introductory material all the way through the calculus proof, which is this video. I would encourage you to watch the other 3 videos as well. In this tutorial, I'm going to show you the optimal level production using calculus and the Lagrange multiplier. I start out putting capital on the y-axis and labor on the x-axis. I'll draw in the ISO cost line and the equation for it, and the ISO quant line, which is a blue line. The optimal level production is right there, but the producer could produce anywhere along the ISO quant line for a given level of production. The producer is constrained by cost. They want to minimize cost and stay on that blue line, so they'll pick a cost. Obviously, it's going to be where the cost line, the green line, is tangent to the ISO quant line, the blue line, at that point right there. And this is where all these slopes are equal to each other. And I'm going to go through this step by step, but this is the final solution. This is what the final solution looks like right here. To do this, there's this thing called the Lagrangian multiplier, and it's signified by lambda. So I have a given quantity I want to produce, and I'm constrained by cost. So I have these 2 equations, the green one and the blue one, and the green one is my constraint equation. I'll set that equal to 0, the constraint equal to 0. And it's typically written as cost minus the rate of capital times capital minus the wage rate times the amount of labor used is equal to 0. Now I set up this big honking equation. That's not an official calculus word, but z is equal to the function of capital plus lambda times the constraint equation. Lambda times the whole thing. Let me move that up just a little bit so I can give myself a little room to work. So I'm going to rewrite this as z is equal to the quantity of capital, which is a function of labor and capital, plus, I'm going to multiply lambda all the way through for all those. This gives me lambda times cost minus lambda times r times k minus lambda times w times L. So now I'm going to take the partial derivative of z with respect to L, and this is equal to the first part of this equation. This gives me the partial derivative of q with respect to L. This means how does quantity change as labor changes? Now I will take the derivative of the second part of the equation. Now that's a constant, and that's a constant because they don't contain an L. So I have minus lambda times w. Now I take the derivative of z with respect to k, which is equal to the partial derivative of q with respect to k. In other words, how does quantity change when capital changes? Now I take the derivative of that part of the equation. That's a constant, and that's a constant because it doesn't contain a value of k. This leaves me with minus lambda times r. Now I take the partial derivative of z with respect to lambda, and this is equal to that part of the equation, which is nothing. It doesn't have a lambda term. Now the second part of the equation, everything has a lambda. So I have c minus rk minus wl. Alrighty then. I'm going to set all these equal to 0. And I am going to solve for lambda. And I'm going to work on these one at a time. I'll do that one first, then I will work on the second equation. And I don't think I'll need to work much on the last equation, but I'll put it there anyway. Again, I'm going to solve for lambda and all equations. So the way I do this, I add lambda times w to both sides of the equation, a little algebra here. And these 2 terms cancel out. So I'm left with the partial derivative of q with respect to L is equal to lambda times w. Now I want to get rid of that w, so I multiply both sides of the equation by 1 over w. So the W on the right-hand side cancel out. This gives me the partial derivative of Q with respect to labor divided by W is equal to lambda. And now I'm going to work on the second equation. I'll add plus lambda times R to both sides of the equation. Those terms cancel out. This leaves me the partial derivative of Q with respect to K is equal to lambda R. Now I want to isolate lambda, so I multiply both sides of the equation by 1 divided by R. The R's on the right hand cancel out, and this gives me the partial derivative of Q with respect to K divided by R is equal to lambda. Woohoo! Now, look at that. I have two lambdas, two things equal to lambda, so I can set them equal to each other. So I let them equal to each other like that. I wonder if I could even say what that is. Let me try. This reads as the partial derivative of Q with respect to L divided by W, or the wage rate, it's kind of hard to say actually, is equal to the partial derivative of Q with respect to K divided by R, or the rate of capital. So now I multiply both sides of the equations times W. So those W's cancel out. So I'm left with the partial derivative of Q with respect to L is equal to the partial derivative of Q with respect to K times W divided by R. Now I'm going to move everything up, give myself a little bit more room to work. Right there. So I multiply both sides of the equations by 1 divided by the partial derivative of Q with respect to K, both sides of the equation. Now this gives me the partial derivative of Q with respect to L divided by the partial derivative of Q with respect to quantity, the ratio of those two, and this is equal to W divided by R, right there. Now if I go all the way back to the beginning and draw in my graph, it's that gray dot right there where those two are equal. So the green line is tangent to the blue line, or the cost line is tangent to the isoquant line, and that would be it.